Thank you, Professor Uchimoto. So we are now in the last talk of these seminars. I decided to slightly change a bit and to have in 1 hour and a half a small view of what we call about corrosion testing, because we talked yesterday about corrosion basis. So now we will see corrosion testing, corrosion monitoring, inspection. We already have a lot of information from inspection, so now we will see what is doing a corrosionist. So I will use my tools and some example about corrosion prevention, but it's mostly like how we can deal with corrosion and what's happened when we change a bit the structure on corrosion. Okay, so if I want to test materials for corrosion evaluation, what I want to do is to evaluate and select new materials, or to find some protective approach regarding always a specific environment and application. So I will ask a lot, I will start to have a lot of questions about, is the testing times that I'm applying in the lab scale is sufficiently representative about what will happen? So sometimes times is long to get some corroded pieces. I cannot wait in the lab, so I have to shortening this. And is the test that I'm applying is really reliable? I mean, sometimes we are simplifying the environment, we are simplifying things, and are they still connected to the real life of the material? The testing of corrosion is also to get information about the material behavior. So the first one is more related to engineers in corrosion. The second one is more for scientists. This is also, in a business unit, the way to have a routine of control of materials and also to discuss with customers about the acceptance or reclamations they can have. And of course, when you have materials, what you want to do is to draw an history about how the material behave in its environment. So that's the investigation. So what we would like for corrosion monitoring is to be user-friendly, simple to install, simple to use, simple to interpret. Okay, able to withdraw with the normal use according to the environment modification, sensitive to onset of corrosion problems. It should be accurate. So we would like to avoid false positive or negative indication. And that's important when we are applying this method later to have inputs in the risk-based inspection and management. Maintainable. So maintainable means sometimes I will use probe that I will insert in the infrastructure. So probes will also corrode, and I need to change them often. So is it easy to change? Is it to access? And actually, this is for the maintenance operation. It should be cost effective. Okay. If we want to have an overview about test method, there is lab scale testing. Here, we would like to accelerate test, try to find model test, tailor-made investigation, and so on. There is also tests that we are applying in service of field of testing. Here, there is a lot of way to do it. Two of them are listed here: exposure coupons, test specimen in process environment. And sometimes, when you are in an advanced project and you start to have a first selection of materials from labs testing, you know that there are only few candidates, and you have a lot of money, you can implant them in the pilot plant. So here you are dealing with the real condition of application of the material. But as previously, you need also to monitor corrosion of these materials to be sure. about their lifetime. So usually when we look on plants, and that is usually what you will find in petroleum and chemical industries, if we are looking with probes. So this morning and the day before, we were aware about ultrasonic methods, eddy currents methods. So I will give some details about how we classify this method in corrosion inspection and monitoring. But for corrosionists, what we like is to insert material, the same material, in the environment, and just to look on this piece of material that we call coupons and or probes. And for these probes, of course, if we don't insert them in the right place in the structure, we will not get the right corrosion rate. Okay, so we have some consideration. Should we implement these probes at the abrupt change of the flow direction, crevice area, adjunction of dissimilar metals? We already discussed about galvanic corrosion. Their position in a high pressure temperature loop, or where we can have a lot of pressure and temperature fluctuation. So this means that to monitor the corrosion rate of a structure, you need to fully understand the structure and what's happened inside. Okay. The funny thing with the corrosion rate is it can change with time. Okay, why it's changing with time? Because a steel, an alloy, is a living matter in an environment. It will create an oxide. Depending about the condition, the oxide can remain or can be dissolved. We have seen that with the basic of corrosion regarding, for example, the Pourbet diagram. So that's something we have to keep in mind. It's not because we have done only one corrosion measurement that we will define one corrosion rate. No, the corrosion rate can change with time. And of course, monitoring, if we are doing some monitoring, we need to have quantitative method, mostly when the materials or coupons are not very accessible. So we have also to think about that. Okay. How we assess the corrosion rate in field condition, and mostly when they are in a complex environment. There is two kinds of techniques, the direct one and the indirect one. The direct one, they are defined as we measure parameters that directly affect the corrosion process. The indirect technique, they provide data on the parameters that affect the corrosivity of the environment. Two different things, okay? These techniques in the two indirect or direct, they can be intrusive or non-intrusive. Let's just give some example. A direct method is measuring the corrosion rate and with time of a material in an infrastructure. For intrusive, that means that I will insert material in the infrastructure. So here, for example, you have kind of electrodes. It's a small piece of materials here inside. And you have a pipe, you will create a hole and you will insert the electrode inside the pipe. So you are intrusive. From that, you will have two ways to characterize the corrosion rate. The first one is a physical. You will weight the electrodes before, after. You will measure the electrical resistance of the coupon, and you can also make some visual inspection. In the other way, there is some electrochemical measurements. So here, that means that, for example, you are fully in liquids. and you can apply the electrochemical measurement as we have seen yesterday. And in this case, you will apply the classical technique like linear polarization, potentiodynamic, electrochemical, impedance spectroscopy, with all the questions that we already listed. So when we are using such kind of, let's say, sensor, or coupons, because I can also put only pieces without to be connected to another measurement equipment, I have a lot of procedure to follow. I have to select the materials and the test specimen. These materials are the same crystallographic orientation. Do they contain some welds? Because welds, there are strains and stress, and they can affect the lifetime of the pieces. Is the history to prepare the material is the same as the materials that I would like to characterize, for example, the pipe, and so on. After, I will ask about surface preparation. Is my material has been prepared in the same way than the material that I would like to characterize on site? And of course, in the testing procedure, you will ask about measurement of surface, weighting. Should I control or not the exposure size? I should inspect the specimen after the testing, and I will determine the corrosion rate, and with the assumption that I should write. Okay. If we just focus on coupons or sensor, and if they are connected to electrochemical measurement, the first one that we can follow parameter is the open circuit potential. Try to remember what I've shown about nickel and copper alloy. One potential was increasing, the other one was decreasing. So it's kind of a trend that can inform about what's happened. Of course, I can write this kind of polarization curve. I try to explain a bit about this. From this polarization curve, I can access to the current of corrosion, so I can have an idea about the kinetic of corrosion. And there is a lot of techniques. And some of them, you can have beautiful maps of reactivity. Just here, this is a current. So that means here there is a high current. In blue, there is a low current. So in this case, some parts are corroding the other one. If you look, we have the high, we can just see that some grains, and actually the high reactivity is on grains. Okay, that's the intrusive technique. I insert a piece of metal that I would like to know the corrosion rate in the system. The other one is, I don't want insert this. One example is quite easy, is when you are working in pharmaceutical chemistry, the point is you want to have the most pure product. If you start to put a piece of steel in the flow, okay, you have some purification step to think about after. So in this case, we are using non-intrusive techniques, and at this time, we will jump to the techniques that has been already well described and illustrated before. I can have two things in non-intrusive. So the engineer will look on the material loss, and for that, ultrasound, eddy currents, radiography, electrical field map. You can have a list. And you can also have to have a look on more local defect, and this is the second one, defect detection. And in this case, you will try to find some techniques that are able to have a good lateral resolution. We have seen that general corrosion is one of the most cases that you can find in corrosion. So of course, metal loss using ultrasounds, eddy currents can be fine. But if you look on pitting, if you look on stress corrosion cracking, for example, so that's very localized phenomena that start. You need more resolution, and for that you will go to, for example, acoustic emission, ultrasonic testing. Okay. That was the direct techniques that you could apply. Intrusive, invasive. Now, the second one is I can detect also corrosion because I will detect a change in something. The first one is I can detect changes in the chemistry of the material. So for example, when I will produce and I will have corrosion product, I will have a change in chemistry of the material. So I can detect that. Corrosion potential is one of the elements. Because the material dissolve, that means that I will have new ions in solution. So if I'm doing some water chemistry evaluation, I can detect them. So there is techniques that are very sensitive, like ICP MS. Fluid detection, that's another point. If the system change, because of corrosion, the chemical composition of the system can change, and it can change temperature and pressure of the system. In this case, if you follow at all time the temperature and the pressure, you can detect any trouble of corrosion. The fouling, the thermography, that the online technique. Offline technique means what? It means that you need to make some sampling of your solution, for example, and you follow with time the chemistry. So okay, so but you will look on what? Water chemistry. If there is any residual inhibitor, so here this is mean like there is some films that have been removed and released in the solution. If there is any chemical analysis on sample. The last one is actually when you finish the experiment, you extract the samples and you are evaluating in the evaluation of chemistry. So what is good is corrosionists are looking for techniques for the others, and the other researchers are always improving their methods. So that's very good because we have the recent improvement of the techniques leads to more accurate evaluation of the corrosion. Now, if you look on the side of the engineer, you will see that it is possible to use a lot of techniques to have an idea what the corrosion rate or the corrosion, if corrosion happens on your material. So in this case, you have to think about one of the first graphs that I've shown between the performance and cost. And here you will have to look on, okay, what is the cost of the techniques that I will use, as I will implement, and what is the information that I can get. So here I took this picture and I'm just focusing on 2 points. The first one is a liquid penetrant. I think Gael Sebald told us about that, and he shows some beautiful picture. So if I look about the cost of the inspection, it's very low. About the cost of the equipment, it's very low. So you go to discuss with the financial manager, he will be quite happy. The problem is, if I look the requirement to understand and to qualify the corrosion from this technique, skills are high, the process control is high, and the process variance is very high. That means that your staff needs to be really trained. And we already discussed about that with the problem of some techniques like ultrasounds and eddy currents that you need to have staffs with certification. The second one is the automatic eddy current testing. So the cost here has been said moderate. The equipment, the cost of the equipment is high. The requirement is moderate, the process control is high, and the process variance is low. So that means that here we already know what we would like to monitor, and we are monitoring always the same kind of defect. Okay? Okay. Of course, if we move from automatic to manual, some items will change, and for example, skills from moderate becomes high. So always kind of balance, and the equilibrium should be fine. So there is variance. For all techniques, actually, there is variance. Here, I'm not fair because I should also introduce a line with electrochemical measurement because they are also inside. And you can see that according to the material, the equipment, the procedures, the calibration step, the criteria that you are choosing, and the human factor, you can have different sources of variance. So some of them are more located on human factors, the other more on the material itself that you are using. So at the end, there is not one unique technique for inspection. Actually, when you think about a non-destructive evaluation process and a technique that should answer to your answer, you have to list at least these questions. Okay, what kind of material I want to monitor? Is it magnetic, non-magnetic, metallic, insulating? What is the size of the material? Thickness, geometry? What are the material conditions? This morning, Professor Feuillard told us about a sensor at for high temperature measurements. So, okay, should material condition in a high environment? Does this material originally have a different grain size, same size? Did they have a residual stresses, gradient of residual stresses? What was his fabrication method? What was his surface condition that can affect other parameters? You see, until the human factors. At the end, who is reading the values that you record? Okay, so that was a kind of small step about, let's say, inspection, that everything is human dependent at the end when we talk about corrosion. And when you start to discuss about corrosion, you need to have what we call an holistic approach. You have to think about all the criteria, the material, the environment that you would like to test to be sure that to be representative. Okay, so corrosion is not a fatality. Sometimes we can try to mitigate corrosion. And actually, why we would like to prevent materials from corrosion, or why we would like to mitigate corrosion. So the first question is, sometimes corrosion happens because the inappropriate material has been chosen. So that means that if corrosion happens, did we select the right material in the right environment? But of course, the environment can change. If the material was suitable for the design of the infrastructure that we have. Okay. And okay, actually, if we are able to change the material or select another material according to the environment, if we are able to change a bit the environment, it will be also good. If we are able to adjust the design, it will be also great. Sometimes everything has been done and we still have corrosion. So we can also apply techniques to protect. So this is the cathodic or anodic protection. I will give some details. And the last one is when nothing of that works, we use a coating or a liner. Professor Uchimoto showed us a question about liners for hydrogen, for example. Okay. In this part of the talk, actually, I should take more time on appropriate material selection and application coatings. Let's see if it's right or not. Okay. Actually, to choose components and metals, it's quite tricky because you have to consider the material itself, the design that you would like to apply to your materials, if there is any manufacturing process, and the overall geometry of the material. That's the first point. The second point is this material will not be alone. It will be connected to other material. So should I have some galvanic corrosion? Think about my small example about copper and nickel, copper and zinc last time. So at the end, I look on compromise. And of course, the compromise is it should also take care about what is the combination of environment and materials. I will not go deep in this table. So when I'm choosing a material, I will ask, okay, this material has a risk of corrosion. What could be the corrosion type that I will face? Is this type of corrosion will change? In one case, if there is some corroded product that appear, can they protect the material, or should I use a corrosion protection method? And is the environmental condition are stable? This last point actually is quite important when you look on atmospheric corrosion. Between winter and summer, the temperature, the pressure, the humidity is changing. And when I'm looking at that, I'm not only thinking about the alloys, metallic alloys that are considered here, but also if there is any other pieces of materials like polymer and ceramics. So, a small example. Here the question was, for a specific application, could we change the carbon steel to be by stainless steel? Okay, that's the question. And what is so first we know the two materials, carbon steel and stainless steel. So right now I know already that they will not have exactly the same corrosion behavior. So what is the media? Okay, here we are working in a carbonate media. So that means it will have a lot of CO3 minus 2 in solution. So now I know that these ions may react with chemical elements of the two steel. In one case for the carbon steel, mostly iron. In the case of the stainless steel, it could be iron and chromium. I will skip the other one for simplification purpose. I know so I have described the materials, I described the environment. Now I will describe the use of the material. They are in tribocorrosion. So I never defined this word. I will define it now. So it's when you apply a mechanical load on the surface of your material in environment. Some people know that it's freighting or tribology, so it's a mixture between tribology and corrosion. So what we are doing now is first we will characterize the materials in the environment. Here you have electrochemical curves that has been plotted in the two environments. So first you know that there is a strong difference. Okay, perfect. I should write CQR. In red, this is a carbon steel. In black, this is a stainless steel. So if you look the curve, and we will look only on this part, for example, you can see here I have a lot of currents flowing from the electrode, here less. So that means that in this environment, in static condition without mechanical load, stainless steel is better. So if I'm applying a mechanical load on surface, is stainless steel still better? So what I'm doing is just I make a test. Here you can have the friction track. at the optical level seems exactly the same. If you look at the microscopic level using SEM, you see that globally we can see the scratch of the sliding. Sometimes some oxide or carboxide species following the roughness of the material. And one of them has higher quantity. This is the carbon steel. Okay, so from the optical observation, it seems that the surface here is less clean than the other one. So we could expect some differences in the material loss. So we are just measuring the material loss, and you see the result actually is exactly the same. Okay, that means that here, for this question, I will not go in details in the equation because actually elements are reacting with the carbonate and change the layer of elements that precipitate on the surface. But at the end, if we try to solve the question, can we use a stainless steel instead of a carbon steel in this environment for this specific application? The answer is no. And it's quite good because carbon steel is cheaper than stainless steel. So here, to solve this question, we have tried to answer several steps that I defined before. Okay. So that was changing the material. Now, if I try to change the environment, so hopefully, it's not always possible. I mean, sometimes you are constrained. But if I'm able to do it, I will play on the temperature, for example, because corrosion is Arrhenius law. So it's the activation energy is an exponential of the inverse of temperature. And I can change also the flow velocity. I can increase the content of oxygen or the aggressiveness of species. I already detailed this before. But sometimes when I'm changing the environment, I can get good or bad results. So here, this is an example. I will go quite fast, but I hope it will be understandable. So here, the idea is to create a new material from a first one. So the first one here is a material containing iron, nickel, chromium, and using technology of dealloying, metal liquid dealloying. Actually, what you are doing, you dissolve the nickel and you just keep the iron and chromium and you generate such kind of ligaments. When you have performed this, actually, you have a new material and you need to stop by a solid state where this microstructure, it's here the micrograph, where you have the iron and chromium, and the black one are the nickel and magnesium, which are mixing because of dissolution of nickel in the magnesium bath. This technology is quite nice because you can tune the microstructure of the ligaments, so you can get at the end porous microstructure with a gradient of porosity in the volume. But the point is, at the end, what you have to do is to dissolve the magnesium, and for that you will use nitric acid. The point when you are using nitric acid in some elements, in some materials, you can show it, it is shown by these two curves. You can observe that there is an improvement of one, the potential, and the other one, the current will decrease. That means that the reactivity of the material after the treatment of the nitric acid is better. So this is because you are changing the surface of the material. So the environment is changing the surface of the material. Unfortunately, here in this case, the environment is a chlorure sodium for the final use, and because you have a porous structure, even if you are trying to reinforce the surface of the material by a passive film, doesn't work. The film remains quite sensitive to degradation. Okay. Another key point for corrosion is the design. So what we can observe in companies and when we are doing expertise is that the majority of the corrosion form is affected by the geometry of the component itself. It can be galvanic corrosion, crevice, erosion. The first here, this is a general guidelines that I took from a reference book. So is the design of the sample or the piece is enough sufficient with a corrosion allowance? Okay, I know that in the infrastructure, the material will corrode. Is the thickness, for example, of the wall of the material is enough? The point is also, I know that I will have corrosion at this place, and I don't know how to solve it. So I know that this piece is kind of replaceable pieces. So if I want to replace this place, is the component is easy to access. So that means here, I already think about the design of the structure. Sometimes, because of the atmospheric corrosion, so the variation of the temperature, pressure, and humidity, I know that I can have a droplet creating on the surface of a material, and I can just try to remove them. This is also the question of hot and cold spot. Remember that I show you that we can have a thermogalvanic corrosion. And this is my pipe with hot steam that was going under the soil for piping system, for example. Can I minimize the consequences of corrosion on surroundings? So here in this place, this is the small graph here. Here I have a pipe. If the pipe flow, it will goes directly on electrical equipment. So I should take a drain to avoid this. Also, I should avoid edges and irregularities in the infrastructure. Easy to say, sometimes more difficult to do. Okay, if I try everything and I try to solve everything, and sometimes I'm not able, so I need to protect my material. So one of the largest way to protect materials, and it's always using for pipe systems, pipe infrastructure, it is a cathodic protection. The idea of the cathodic protection is apply an external current that will immune the material. So the potential has to be really well selected, and there is a lot of works, and there is a very specific knowledge to reach to apply this potential, because if you slightly shift this potential, you can move the material from an immune domain to a pitting or crevice domain that you should avoid. So the cathodic protection, how does it can be applied? You can apply this using an external source. Okay. You apply a potential by current, no problem. But you can also do it using galvanic corrosion. In this case, you will connect to the material that you want to protect another material that will dissolve more easily. This second solution, for example, is well known for in marine application. the last point is important, is if you apply cathodic protection, you have to look, so you have to be sure to be far from the pitting and crevasse potential, but you have also to avoid on the other side of the diagram, cathodic disbanding. So here it's if the potential is too low, the interface between a metal and a bond coat, for example, will start to delaminate, or you want also to avoid hydrogen embrittlement. Still a compromise. Last solution, and I think I will, no, it's okay. That will be my last slides. It will be about coatings. Okay. I will now apply a layer on the surface. So I mean, now I have a multi-structure material. What can be the properties of the coating that I have to select? The first one is this coating could have a barrier effect. So what is the meaning of barrier? It's meaning that you want to avoid any gas diffusion, liquid diffusion, or elements diffusion. This coating can act as a cathodic protection. The coating will dissolve, and until the coating remains, you will protect your material. The coating also could have, the others could try to limit the dissolution of the material. These coatings, they can be metallic, inorganic, or organic. So I will just discuss metallic, and I will give one example of organic coating, which has not been yet applied. Okay, so now if I move to the metallic coating, so just to be sure to be all focus on the same thing, is my substrate, it's a metal. Let's say here it can be iron or aluminum. I will put a layer on it, and I will have the solution on the top. I have three ways to select a coating. I can select an inert coating. Inert means that it doesn't react with the water. If you remember what I said before, some elements like gold and platinum are suitable for such application. You may be rich to apply them. I can also apply another coating, a nobler coating. So here, that means that this coating, nobler coating, will react with the environment, but it can protect the substrate. Let's give an example. I can have, for example, steel, carbon steel, which quietly corrode in general corrosion. And if I put a stainless steel coating on it, I will avoid the general corrosion of the carbon steel. The last solution, and this is sometimes the one that we prefer, is a sacrificial coating. So in this case, I know and I drive the system to the coating that I'm applying should dissolve. As long as I will have a coating, my substrate will be protected. One example is a galvanized steel. This is a zinc layer on a steel. Zinc will dissolve and the steel will be protected. So here, this is my potential scale, more or less visible. And this is just to give an idea, to remember what we have said yesterday. My idea is to protect iron, for example, here. So if I have iron, what I will do is I will use materials with a lower potential, so potentials that are below this iron, and can be either aluminum or magnesium. When I'm saying that, that means that I already know that the thickness of my coating will be a key point in my infrastructure, and I will not anymore characterize the or monitoring the substrate, but I will monitor the corrosion rate of the coating. Okay. There is a couple of ways to produce coatings. In the last 10 or 20 years, the cold spray technique was quite used. Why? Because it changed a bit compared to other spray technique where we were melting particles that were flying to the surface and attach. Here we are using physical bondings, so that means that the particles that we have selected never change of physical and metallurgical state, which is quite good because in the process that means that there is no evolution of the chemistry of the particle. Okay. One point with this technique is the particles that you have selected, usually they are more or less cycled, but when they will impact the surface, they will highly deformed. So that means that you mostly keep the chemistry, but the deformation of the particle are change. So that means that the stress on the particle, so the mechanical deformation of the particle is changed. So that means that for some application, there is some limitation. And for example, for when you look on the tribology, for example, for wear resistance, this coating are not so good. The point is to improve this, you can have some mixing coatings. So in this case, you will have a dual phase microstructure. So that means that you can mix powders between them and to create or to design specific coatings with properties. So in the case that I will report here, the idea was, okay, I want to protect an aluminum substrate using a sacrificial coating. And for this one, I want to use a specific aluminum composition. And I know that this coatings needs to be slightly more dense, slightly more wear resistant. So I will insert during the coating elaboration silicon carbide. And with that, I would like to get better corrosion resistance. So now, if I want to understand if I will get better corrosion resistance, I will first describe the metallurgy of the powders that I'm using, and I will also characterize the coating itself, so its crystallography, roughness, composition, porosity. Here, an example of the aluminum powder, a beautiful SEM image of a spherical particle. In this technique, there is also a key point, which is the distribution size of the particle, which can be quite important. And also, because this is a physical adhesion, we should not have thick oxide layer on the coating that we have also to check. Oxide, why? Because oxide limits the interaction between the metallic atoms during the elaboration process and when the particles impinge the surface. Okay. Let's say we fix the size of the particle, of the metallic particles. Now there is a parameter on which we can play is the silicon carbide size. Okay, here in this study, we were playing with several size of particle, of silicon carbide particles, small one, let's say medium one and larger one. And you can also mix with different volumic fraction. At each time when you change a parameter, you know that you may change the corrosion behavior of the system that you have. So the question that we will try to answer is, we want to have the compromise performance. So These coatings may protect the substrate from corrosion. So that means that during the process, which is time limited, using a certain quantity of matter, we want to have what? The thicker coating, the denser coating, and the less porous coating. Okay, thick, it will remain longer in the solution. I said what? Thick, dense, and less porous, they are mostly the same. That means that I have less defect in the volume of the coating, so the diffusion of water through this coating will take more time. There is a lot of physical characterizations that we can do to describe the coating. I will not go into detail. The point is when you change the particle size, you change the roughness. You change the roughness. Roughness can be a factor that change some NDT results. So you have to keep that in mind. It change this one is roughness. Both are the roughness actually. One is depends about the quantity of the particle. The other one depends about the size of the particle. Okay, the good point is even if you tune a bit the process, you don't change any microstructural, you don't have any microstructural evolution of the aluminum particle that you protect. Oof. You keep aluminum, that's what you want to do. There is no oxidation because oxide, sometimes you want to avoid them in the structure. And you look on the micrograph of the cross-section of coatings that you get, and you look on defect. So where are distributed the reinforced particle, so silicon carbide, and you can start to have a map about, okay, I design a coating. And this coating are quite different. Sometimes silicon carbide are just sprayed like that. Sometimes they start to be very interconnected. Sometimes they are very big, so there is only small layer of alumina between particles. It may change the corrosion process. Okay. There is also another question. It's if we are going deeper, we can see that sometimes there is decohesion between particles and the matrix of alumina. That means that there is porosity, inherent porosity to the system, but also there can have some porosity due to a bad adhesion between particles. So you generate new defect that you try to avoid during this process. What is good is when you use non-destructive technique, you can get a real evaluation of porosity in volume of the matter. And here you answer one question, is the porosity are interconnected? Because if they are interconnected, they are creating a preferential diffusion path for water and corrosion start on your substrate. So here it's X-ray tomography. We have been teach about that a little bit before. Okay, so in this study, the idea was to find the best compromise and regarding some microstructural porosity, metallurgical parameters, and we said, okay, 30%. Okay, so it should be the best candidate. Let's have a look. Now, if we immerse this coating in solution. So first, I said, for corrosionist, this is the open circuit potential, so just following the potential of the material immersed in solution with time. And let's see what's happening. Here, you have the aluminum. Mostly stable, nothing happens in the solution. Here, you have the coatings. So That means that coatings are more reactive than the substrate. That you want to have actually, because coatings may be sacrificial, so they may dissolve. This curve say, okay, it will dissolve. Perfect. Now you want to have an idea if it will have a difference in corrosion rate on the different coatings that you prepared, and actually, except at the beginning, everything is the same at the end. Why it changed a bit at the beginning? It's because the morphology of your coating is not the same, because you have more or less silicon carbide. The porosity is not the same on the surface. Okay, and the link between the silicon carbide particle and aluminum are not the same. Okay, but this is just a thermodynamical trend. What I want to know if it's dynamically, so in terms of kinetic, if my coating will dissolve faster than the aluminum. And actually, this is the two curves here. So they are plotted not anymore in the American standard, but in a European standard. And if you compare these two curves, actually, you just have to point this point and this point, and you can realize that going to this pure aluminum to the aluminum coating, you increase the current density, you increase the corrosion rate. Okay, so corrosion rate is increasing as previously, yeah, because corrosion rate is sensitive to metallurgy, porosity, roughness, and so on. Okay, the point is same behavior for all the coating. So that means that we find, from a metallurgical viewpoint, a coating which was 30%, which has something like best condition. But if we look on the corrosion rate, you can choose what you want. It will have exactly the same behavior. So that's from the engineer part. I will say, okay, you can do what you want with the coating. You can select whatever the composition you want for your coating. You will get exactly the same result. So now if I'm moving from the researcher, so researcher want to know how corrosion goes to this material. So for that, our PhD student has done coupons, immerse, and she remove coupons with time, make cross-section, and observe the corrosion propagation. So here you have the corroded layer, the uncorroded layer, and you can see that the thickness of the corroded layer change according to the composition of the material. There is also some corrosion product that appears on the surface. Okay. One question she asked was, okay, so initially this process lead to a very rough surface. So if I'm able to remove this initial rough surface, should I have a difference in corrosion rate? She checked, and yes, there is a difference in corrosion rate. So that means that this process alone is not sufficient. If you want to mitigate this corrosion, the corrosion rate of coatings elaborated by such kind of way, you need also to eliminate the initial roughness. And you can change the, I will not say significantly, but enough, the corrosion rate of the material. Okay. So now another question is, okay, I know that I have defect in the coating, they are randomly dispersed. So is the corrosion will go to this defect preferentially, or is the corrosion moving like a front of diffusion? And if you look the images that has been taken, mostly it's kind of front of diffusion. There is no specific path for diffusion. However, from the basic and first mechanisms of corrosion, if we, from the observations that she have observed, she found that there is at least some specific diffusion path, and the water goes to this specific path, let's say destroy the adhesion between particles, move also not only in the depth of the coating, but also laterally to the coating. And at the end, you have always a uniform front of diffusion with a modification of the chemistry, of the solution that increase locally the dissolution of the material. And sometimes you can have, let's say, parts of the materials that are totally removed because of this lateral dissolution phenomena. But at the end here, if we want to avoid or limit corrosion, the key point is roughness. Okay. So I said that this one was for metallic materials. So now just a few words about polymer materials. And so polymers materials, you will find a large variety of polymers. And this study, which was a double degree PhD student study between Tohoku University, CNRS, and INSA Lyon, actually we were using the epoxyamine material as a reference, and our colleague from the chemistry was able to replace amine by other chemicals. So here we are not anymore we are not yet in the frame of coatings. We just try to evaluate actually a mechanism of degradation of polymer, which is the water uptake. So when water diffuses to the polymer volume. For that, we prepare, actually our PhD student prepare samples. We use a way to emphasize and to increase the diffusion rate of water using oven. So all the experiments have been done at a specific temperature. And to monitor the water uptake, we should choose two techniques. The first one, which is well known and the corrosionist like, is whitening. So we have coupons. We just measure the mass of the coupons with the evolution, with the time, and you will get evolution, which is quite good. But that means that if you are on site, you will have intrusive technique. You will need to put coupons of polymers in the system and to follow the evolution of mass of polymer, which is not suitable in many cases. So you have to think about other techniques to evaluate the water quantity in this polymer. In this case, it was capacitive measurement, so using dielectric properties of the evolution of the dielectric properties of the polymer. What were the results? So here the question is, can we have a reliable technique to evaluate the water quantity in the material? The first graph, which is on the top, is a mass evolution of a coupon. And at the same time, our young colleague was performing capacitive measurement to get the relative permittivity evolution of the coupons with time. Roughly speaking, you can see they are almost the same trend. There is some variation, but almost the same trend. And if you look only the black and blue curves, you can see that in both cases, the black curve is above and the blue curve is below. What is the main difference between these two curves is the black one has amine as a hardener, whereas the blue one has another hardener, which is an ionic liquid. So by changing the nature of the chemical elements used for the polymer, you will change what? First, you change the kinetic of diffusion of water inside the polymer. And also, if you look the value at the end, you change also the saturation of the polymer by water. Which is good with these two curves, and mostly with the first one, is you can access to diffusion coefficient and mass saturation of after experiment. So you have quantitative information regarding the properties of the polymer and their resistance to water uptake. Of course, you could apply the same method to capacitive measurement, and here the idea is to say, okay, so I know that I can rely on capacitive measurement, so I can use the permittivity of the material as function of time as a parameter to follow any evolution of water content in the material. And saying that, I can choose a right non-destructive technique to evaluate these properties when I'm on site. I think I was a little bit short, but I know I'm arriving at the end of this lecture. So just to make a summarize about the 3 lectures that I gave, I try to answer to what is corrosion, where happened corrosion, who is corrosion, how take place corrosion, and, sorry for that, why it is important to implement corrosion issues in risk-based inspection and management, because it is also a key player at the same level than mechanical damage. Okay? So, but of course, we have to remember that it contributes to the certain level in damaging of the material, and corrosion alone doesn't happen not often. You always have to, it's a contribution. So you always have to think about, okay, there is corrosion, but it can have another parameters that can affect corrosion, and both of them, they are going to what we call the synergy of action. And when you talk about synergy, that means that whatever you are whatever the infrastructure you consider, if you want to think about its durability, it's very important to have an holistic approach. So holistic approach means you should have an overview about all the parameters that can affect the system to find solution, either to mitigate corrosion or to monitor corrosion and to follow the evolution of the system. And I'm really sorry because I was too short. Thank you very much.